Everyone, welcome to my class. Today we are going to discuss the summary or highlights of chapter 4, engineering mechanics. Let's see what are there. So in engineering mechanics there are statics, dynamics, strength of materials, and mechanism kinematics. So for statics, main concept is on an equilibrium or static system, the force from all sides are balanced. Hence, total force must be 0. For dynamics, displacement is as a function of time and force. A strength of materials, we can measure how much deflection occurs if we impose a force on it. So delta is the deflection, is function of F. And vibration is also similar to deflection, is function of force, F. Okay. So this one, how quickly or lessly they vibrate. It depends on the force applied. Now, general principles here, basic quantities and their idealization for mechanics. So, we will learn the Newton's law of motion and gravity. Okay. And after that, the international system units or SI units. So, the outline is mechanics, fundamental concept, SI units, calculations, and analysis. Now, mechanics. Mechanics is usually divided into 3. Rigid body mechanics, deformable body mechanics, and fluid mechanics. So let's go for rigid body mechanics. It deals with statics, means equilibrium of bodies at rest, or if the body moving with a constant velocity. And dynamics is accelerated motion of bodies, means it's moving with some acceleration. So the quantities, basic quantities are length. We know length is a distance from one point to another point. So for mechanics, it's a position, okay, position or location of a point in 3D space. Mass, measure of a quantity of the matter, usually in gram or kilogram. Okay. Time, succession of events. Okay. And then force, a push or pull exerted by one body to another. So usually for mass, this is a scalar quantity, but for force, it's a vector quantity. We have to mention because the mass can be converted to force also if we multiply by g, the gravitational acceleration. Okay, so idealization, what is particle? Particle is a tiny in size, it's a mass, and then usually it's too small, so can be neglected. What is body or rigid body? The body is a combination of a large or huge amount of particles together. Concentrated force, when we apply a force to a particular point focused, okay, then the effect of loading is much more. That's it. That is concentrated force. Now let us see the Newton's law of motion. There are 3 laws. First law is when a body in equilibrium, all the force acting on the body, okay, will be balanced and the total force equals to 0. Okay, the body will be in a static position or moving with a constant velocity v unless we imply some external force on it. Okay. So, second law is a particle acted upon an unbalanced force or a force applied on a particle in a certain direction, and there is a acceleration, then the force will be, what is the mass multiplication, the acceleration, F equals ma. And the third law is every action has a equal and opposite reaction. So, for example, here two body A and B collide to each other, the exerted force by A to B and by B to A will be equal and in opposite in direction. Okay. Now, let us see the vector. So there are scalars and vectors and some vector operations. Okay. Position vectors. What is the force vector along a line and unit vector? Then products. We'll see here. So let us see first the scalar. A quantity which has only the magnitude of value can be either positive or can be negative. That one is a scalar. For example, okay, mass, volume, length, they are scalar. Now, vector, a quantity that has both magnitude and direction. So, position of a point is a vector, like GPS position. So, we know there are X, Y, and Z direction. Force, moment, okay, they are all vector. It has both magnitude and direction. Here to mention, mass is a scalar, but weight of a body is vector. Okay, so weight will be mass multiplication g, and it can be expressed in terms of Newton, the unit will be. Okay, so vector can be subtracted or added to get the resultant vector. Suppose A is a vector and B is a vector. If we want to find out their subtraction, okay, A minus B, so we can represent in a parallelogram and then use the parallelogram law to find the vector subtraction. So B is, this is the direction. So if we say minus B, the direction will be opposite. So this we can represent, whereas A can be represented this. This also can be shifted to this side because they are parallel. Okay, and then through the parallelogram law, okay, A plus minus B will be R or R dash. So R dash equals A minus B. Okay. Another one, if we want to add, find the addition, the resultant force. Suppose there are two forces, F1 and F2. If we represent in terms of the sides of a parallelogram, F1 this and F2 this. So resultant force Fr or F can be represented as shift this force F2 to the other arm of the parallelogram, and then this one will be this plus this. Follow the triangular law. Okay, so this how we can add and subtract the vectors. Now, in Cartesian components, so usually, for example, here a force is F along the x direction. the component or the value of this force is Fx, but direction is I, usually along x-axis. The direction is represented by I, while along the y-axis, J. If it is three-dimensional, then z-axis it will be K. So what is the value of Fx? Fx equals, what is this length? This is the magnitude of the force, F or modulus F. So Fx will be F or modulus F cos theta, if this angle is theta. Okay? And then Fy will be F sin theta. So we can represent this vector F in terms of Cartesian components, means Ij, Fxi plus Fy. Now, suppose there are three vectors here. One is F1, one is F2, one is F3, and it's all two-dimensional. And F1, the value is represented by F1xi plus F1yj. F2 is this, and F3 is this. How we can get the resultant force? Resultant force will be Fr. So this one will be F1 plus F2 plus F3. Okay, and we can write this one Frxi plus Fryj, because I component and j component. Now, what is the value of Frx? If we add these three, first the I component, F1x minus F2x plus F3x. This is the value of Frx. You can see this here. Same Fry. Similarly, all the j component. We add, this will be the value. This is how we can add or subtract the vectors in Cartesian component. All these are the coplanar forces or vectors. Why? Because they are on the same plane, one plane, xy, not three dimension. Now let us come in three dimension. In three dimension, a vector, for example, there is a vector A. It has three components: ax along the x-axis, direction I; ay along the z-axis, direction j; az along the z-axis, direction k. And if we consider the angle of this vector A with x-axis alpha, y-axis beta, and z-axis gamma. So these are known as direction of the vector A. Okay, and this is orientation. Usually, these angles alpha, beta, gamma will be more than because from this triangular figure, cos beta ay divided by a modulus a, and cos gamma az divided by modulus a. So if we want to find a unit vector, what is unit vector? A vector whose magnitude is 1 and direction in a particular direction. For example, what is the unit vector of A? A vector whose magnitude is 1, UA, denoted by UA, magnitude is 1, for example, like this, and the direction along direction of the vector A. How we can get and the unit vector? Unit vector is, if we know the magnitude of the vector A, modulus A, divide the vector with modulus or magnitude, we can get a unit vector along the direction of the vector. So unit vector along vector A is UA equals A divided by modulus A. Okay. So in Cartesian, A has three components. Okay. Let me write here. So A has three components. A equals x I plus a y j plus a z k. If it has three components, so this is the vector A. So u will be A divided by A, modulus A. Okay. What is the value of the modulus A? Modulus A, I will show next. slides, never mind. So if this one x divided by a means this is the modulus a. Ay divided by modulus a, az divided by modulus a, direction I, j, k remains the same. Okay, so this is the unit vector. Now, the vector a can be represented by modulus into ua because its magnitude is 1. Now, let us see. This unit vector can be represented as cos alpha I, cos beta j, cos gamma k. So, what is the cos alpha? Value of cos alpha x by a. Okay, cos beta ay by modulus a, cos gamma az by modulus j. And one characteristics of this cos means cos alpha, cos beta, cos gamma are known as direction cosines because this is cos. Alpha, beta, gamma are directions of a vector. Okay, so one properties of this direction cosines are cos square alpha plus cos square beta plus cos square gamma equals 1. You can try, because cos alpha value is this, cos beta value is this, cos gamma value is this. Okay, so since ua is magnitude 1, direction same, so we can write a equals magnitude a into ua. Means it's like that. Same axi, ayj. Okay. Okay, let's go ahead. Now let us see one example. Find the value of alpha and express the force as a Cartesian vector, okay, from this figure. Okay. So figures, there are two angles are specified. One is beta. Beta is angle with y-axis 60 degree. Another one with z-axis 45 degree. Okay. But alpha with x-axis is not given. So how we can find out there? We can find out from this formula, the log. Okay, so we know this one, beta is 60 degree, gamma is 45 degree. So we can calculate and find out the value of cos alpha equals plus minus 0.5. So alpha will be cos inverse 0.5. This value can be if we take the positive 60 degree, if we take the negative 120. But by inspection, we can see that alpha is 60 degree, not 120, because effects are in the positive x-axis direction. So we know this alpha equals 60 degree. Now, what is the value of the force? Because it's asking force. Here is given magnitude is 200 Newton. Direction is not. Direction this. So we find out already. Direction is alpha, beta, and gamma. So direction cosine, cos alpha, cos beta, cos gamma. So what is F? F will be F. This is the magnitude cos alpha I, F cos beta j, F cos gamma k. Now we know alpha, beta, and gamma angles. Alpha is 60 degrees, so 200 cos 60. Beta is F value is 200 Newton. So beta is 60 degree. So 260 and gamma is 45 degree. So it will be 100 I plus 100 J plus 141.4 K Newton. Okay. This calculation, is it correct or not? We can check that one. How? Let us find the magnitude of this. So magnitude, I told you, magnitude or modulus F equals fx square plus fy square plus fz square, then square root. So fx is 100, fy is 100, fz is 141.4. So if we calculate, this is 200 Newton, means our calculation is correct. In this way, you can verify that your answer is correct or not. Okay. Now let us see position vector. So position vector means is the vector for a point. For example, here is the point P. P is x, y, z. It's started from the origin or O. So what is the position vector? Position vector means is pointing the vector OP. It started from O, 0, 0, 0 to the point P. Sometimes this can be written R. So R equals xi, yj, zk. Okay, this is the position vector. So along x-axis, the component is x. Along y-axis, the component y. Along z-axis, component z. Okay, and the vectors. So again, for F force, F can be formulated in terms of Cartesian position vector. This is the position vector in Cartesian form. So if this is a force F from A to B, and we know the magnitude, we can find the magnitude, multiply by U. What is U? U is a unit vector. Now, let us find the position vector of this. Position vector is R. What is a unit vector? If we divide R by magnitude of R, means R divided magnitude R. This is the position vector. Okay, means this is the unit vector. So U means R divided by R. So this is the vector in terms of the position vector. We need the unit vector. Now let us see one example. Okay, one man pulls a cord with a force 350 Newton. Okay, and this force acting on the support at the point A, okay, as a unit Cartesian vector and determine its direction. So what is the R position vector? A and B. From inspection, we can find that A is, okay, X is 3, Y is negative, because this is positive. The position is here, negative 2. This the B. B is 3, negative 2, because this side, and distance is 1.5. This is the 1.5. Now, the other one for the A is the on z-axis. So, X is 0. Y also 0. Only it has z component. The component is 7.5. Okay. So, position vector is B minus A. B minus A means I component, J component, and K component. So, B is 3 minus 0, I. Y component is minus 2 minus 0, J. Z component is minus 1.5 minus 1.5 minus 7.6. Okay, so this is K. So after calculating, we can get the position vector 3i minus 2j minus 6k. This is in terms of meter. Now we have to find out a unit vector because it's asking the unit Cartesian vector. So unit vector U equals R divided by modulus R. So modulus R equals, okay, and the I component square plus j component minus 2 square plus k component minus 6 square, then square root. We know this is the modulus or magnitude. So equals 7 meter. So unit vector will be R divided by R. R is this. So 3 over 7i minus 2 over 7j minus 6 over 7k. This is the unit vector. And now from this unit vector, we know one thing. What is the direction cosines? So direction cosines are, let me write here. Okay, direction cosines are, from there we can write cos alpha, okay, cos alpha I cannot write alpha, so I'm giving A. Cos A is the alpha. Let us consider cos alpha equals 3 by 7. Cos beta, beta I'm taking B, equals minus 2 by 7. And cos gamma, I'm taking for the gamma G equals negative 6/7. How these are coming? These are coming from here. From here. 3/7 cos alpha, cos beta, negative 2/7, cos gamma, negative 6/7. So from here, we know cos alpha, cos beta, cos gamma. Easily we can find out the value of alpha, beta, and gamma. So cos inverse this, cos inverse this y component, negative 2/7. This one will be beta. Cos inverse, negative 6/7. Okay. Okay. Now, the equilibrium of particle, or from here main concern is the free body diagram of a particle, and we can solve the particle in equilibrium. Okay, if there is in equilibrium, and with the problems like particles in equilibrium, we can solve using equations of equilibrium. So first condition for the equilibrium of a particle, then free body diagram. Can be coplanar system, means one plane, can be in 3 dimensions. So let us see what is free body diagram. Free body diagram, when a body in equilibrium, how the forces acting on it, and balance the body so that it is in a static position. So for example, this is a linear elastic spring. Okay, so spring constant or the stiffness is K. What is the force acting on this? F equals Ks. What is S? S is the displacement if we pull the spring. Without pulling, without force, because it will be for the weight, it will be until this LO, initial position. After pulling, the displacement is S. Okay, so this. Okay, cables and pulleys, they are example of free body diagram. Okay, and cables are assumed negligible weight. Cannot stress. Tension always acts in the direction of cable. Okay, for example, this. Okay, tension force must have a constant magnitude for equilibrium. For all the forces, they must have the constant magnitude for equilibrium. For any angle, the cable is subjected to a constant tension. So, how we can draw the free body diagram? Draw outline shape. Outline of the shape. Show all the forces. Identify each of the forces with its direction. So that's the main how we can draw the free body diagram. For example, here one sphere is hanged with some support as shown in this figure. So weight, mass is 6 kg, and then supported by a spring fixed on G, one knob at point B, and it's fixed, the string is fixed at the point A, and there is a knob where at C the sphere is hanged. So if we say draw the free body diagram of the chord CE and the full system, how it will be? First, if we want to draw, first we have to draw the sphere with knob. Okay, sphere with knob. Now, what are the forces acting? One force due to its mass, or we will say for the mass there will be the weight towards the center of the earth due to gravity. This we say gravitational force. Another one acting upwards, EC direction. So FEC is up and the weight is downwards. Now, what is the weight? The mass is given 6 kg. So I'll show you this one. Okay. Mass is given here 6 kg. So what is the weight? If we say weight, W equals M is the mass, G is the gravitational force. Okay, so this equals M is 6 kg, mass must be in kg, multiplication, gravitational force is 9.81 usually. So together, if we multiply, it will be 58.9 approximately. This Newton. What is Newton? Because kg, and then for the multiply by the gravity acceleration, g is meter per second square, so it's 59.9 Newton. So weight in terms of Newton, mass in terms of kg. Okay, so this is how we can draw the free body diagram for the chord. Now for the full, we can write again. First, this knob, okay, at the point C, one force FC, which is the weight of the sphere working downwards, another towards the point C due to spring. So this one FCD, one more from C to B and A. So this is another force. Here angle is 60 degrees. So FCBA. This is the free body diagram of the full system. So this is how we can draw the free body diagram. Okay, let's see another one. A cylinder hangs from the point B and supported by two cords at A and C. If we ask, what is the free body diagram of this cylinder from the point B and the full system? So just like before, we have to, but here is given 60 kg. 60 kg means 60 multiplication 9.1. That one will be the weight, which is working towards the center of the earth due to gravity. So for the part 1, it one will be, here will be the B upward, the force or the tension, because it is in a string, can be tension or can be force, can be right anything. So it's the dB, okay? And downward is working BD, downward, the force working BD. BD is 60 multiplication 9.8, this one Newton. And the upwards, we can just write the force, dB, okay? This one is this one actually. This one we can write dB. And it should be equal, okay, to balance, that's why. Now, for the full system, okay, this is the point B, the knob we have to draw downwards, the weight TBD, tension 60 multiplication 9.81 Newton. One more force along the point C, you can say TBC, okay, with angle 45 degree. Another force we can say T, tension of force, TBA, okay. This is the angle we give him. So this is the free body diagram of the whole system. No need to draw this rectangle. You can just show the forces acting and show the axis X and Y. Okay. Now let us go for moment of force. Okay. So we will here mainly focus how to calculate the moments, mostly the scalar moment. Okay, so what is moment? Moment of a force about a point, either can be point like this or about the axis, okay, can be measured. How much force is applied for a body to rotate? Multiplication, the distance from the body to the force, perpendicular distance, so FD. Now, what is moment? This is a tendency of the force to cause the body rotate around the point or around the axis. For example, the door. If we want to close and open the door panel moves around the axis. Okay. So, and then there is a torque. So what is the torque? Tendency of rotation caused by the force. Okay. For example, along the x direction of force or simple moment, we can say the m naught. Here you can see the m naught along the z direction is moving by the force F, and the distance is d from a point O. So m naught will be F multiplication d Newton meter. The distance must be in meter and force is Newton, so Newton meter. Perpendicular distance, and O is the line of action or point of action. Okay, what is the direction? Direction of a movement always follow the right hand rule. So if our fingers are along the movement, we can see from here, and our thumb, what's the direction of the thumb? This is the direction of the movement. So another one, we know the product of vectors. So there are two types of product, dot or scalar product and cross or vector product. So here I am showing the cross product. Okay, if A and B are two vectors like this is the angle. If we do A cross B, again it follow the right hand rule. So direction will be perpendicular to both A and B. So how we can calculate the A cross B or the vector product of two vectors? If A equals AXI plus AYJ plus AZK and B equals BXI plus BYJ plus BZK, A cross B will be IJK. Then component of A, AX, AY, AZ, and then components of B, BX, BY, BZ, which we can express like this, because this is a determinant form. So we can express I equals this row column and this row cancel out AY, BZ minus AZ, BY. Okay, minus J, this column, this row cancel out AX, BZ minus AZ, BX. Okay, and this one plus, plus K into this column, this row cancel out AX, BY minus AY, BX. Okay. So this how we can calculate. So moment of the force, usually moment in terms of vector notation R multiplication F. What is R? R is the position vector. Okay. Suppose here, if it is the R, then R is the position vector. And F is the force. So position vector means for the point P, X, Y, Z is R, X, I, Y, Z, Z, K. This we have seen before. Okay. So if we do the cross product, we can find the moment. And then we can express that one like that. Okay, now let us see some example. So example, this one, calculate moments for person A and B about the point P. This person playing seesaw in a playground like that in the figure. And then give your opinion about the balance status of the system. Now, what we can do, okay, I will come back this one later. Let us see how we can calculate the moment. So, if a point here given and a force working at a distance on a plank. So, according to force, this one will move towards the force. How much it will move? How much the moment? We can find out. The moment equals this one perpendicular distance. Okay, so the distance d multiplication the force. Force is 10 Newton, distance is 0.5. So 5 Newton meter. So this is the moment. Now for balancing a system, both moment, if there are two side moment like this one, here is moment due to this person A, here is a moment due to person B, both should be equal. Then it will be balanced. So we can calculate and then see. Let us calculate here. Okay. The moment for person B. Okay. I'm writing MB. MB equals 500 Newton multiplication 2 meters. So it's equals to 1000 Newton meter. Now, what is the moment for the person A? I'm writing MA equals, the force is 1000 Newton multiplication, the distance is 1 meter. So this one will be again the same 1000 Newton meter. Okay, since the both moment on the right and on the left side, they will be in equilibrium position. Okay, so that's, we can say that they will be in equilibrium position, but here mark something that this person, the weight is half of this person. So the distance is longer from the point P. Okay, this one, the distance is 1 meter, whereas this one 2 meter, means half. This distance is half because the weight is double of that. This means if this means the weight is, or the force is less, and we apply the force close, moment will be less. If we apply further from the point of axis, the moment will be more, and we need less force. That's why. So that is the trade-off, means the force and distance. Okay, and very easily we can see 2 meter distance. That's why it's same. They are balancing. If this person moved to 1 meter, then it will be only 500 Newton meter, and this seesaw will start to move towards the person A and touch the ground. Okay, so this is the trade-off. Okay, let's go to the next. Okay, we have seen this one to calculate the moment, and now another one. Okay, calculate the moments for forces at A and B. Okay, for this position about the pivot or the point P shown in this figure. Okay, so then find the value of force F if the forces are in balanced position. So now let us see what is the moment for force F at the point A. F multiplication the distance, okay, in Newton meter. What is the moment for the force 5 Newton at point B? 5 into 0.5, 2.5 Newton meter. Now, since they are balancing, both moment left and right must be same or equal. So this one equals 2.5. So easily we can get the value of F. So 10 Newton meter. Now this, then give your opinion about the balance status of the system if the force F is shifted 0.5 meter away to the left, means here, from the point P. So let us see how it is. So moment of F value we know 10 Newton meter, moved here, then the moment will be 10 multiplication 0.5 means 5 Newton meter, which is double than the moment at the point B. So we can say that this moment is more, this one means more means double than the moment at the point B. So the system will not be in balance. Okay, the system will start to turn towards the left, okay, and fall until it touches the ground. Okay. That's all for today.